Hello, good morning, good afternoon, good evening, depending on what time you watch this. Welcome to this talk through lesson on Arrhenius equation. So, initially, in the first part, we are going to be looking at maths expression that involves logs and lns, the natural logarithm, sometimes expressed like this ln. So, for those who are really familiar with these expressions involving logs, lns, and you may find it helpful to skip that part because we are going to look at how very simple manipulation of equations involving logs and lns. So those who are actually doing maths at an advanced level will find that not necessary. So you may want to skip the video. So skip the video between these times 10:45 to 7:23. The rules and ideas about logs, lns are covered. You can skip that this section. So initially we are going to look at what an Arrhenius equation is, the general um, structure of the equation, and know various parts of the equation. The Arrhenius equation looks like that here. That is the original form of the Arrhenius equation. Okay, but we're also going to look at the other form of the Arrhenius equation, which is the log form, ln, natural logarithm. So the same equation as above here can be written in this form. So we're going to look at this general these two forms of Arrhenius equation. One is here, and that's the second form. We'll also look at the rearranging of that equation, how to convert that to this, the original form to this form. So we're going to be learning about that. We're also going to look at calculations involving Arrhenius equation, how to rearrange this equation here. So rearranging both forms of the Arrhenius equation, not only the logarithmic form, but mainly logarithmic version of the Arrhenius equation. We are not going to be covering this part here in this video. We'll be looking at Arrhenius equation part 2 for this part. So this part is not covered in this video. Okay, so what we are looking at in this section, in this video, you may consider this as part 1 of the Arrhenius equation. Okay, so this is part 1 of the Arrhenius equation. We'll be covering that and this. We'll also be using this equation, rate equation, that we already learned from previous lessons. So you should be really familiar with this. We're not going to cover this in much of a detail, but we're going to be using this equation. Now, as you know, rate of reaction depends on concentrations of the reactants. Okay, it can be depending on just one reactant, and that superscript is the A gives the order of the reaction with respect to that reactant, and B gives the order of the reaction with respect to that reactant. Okay, the overall order is that plus this. Then you have the rate constant, and the rate of the reaction is given by that expression. Okay, now we know this constant, this remains constant, but what we are going to look at through Arrhenius equation is that this remains a constant only with constant temperature. So when you change the temperature, the K, which is the rate constant, does change as well. So this does not stay constant when you change the temperature. So the other factors can actually affect the rate constant. Okay, so we're going to be looking at mainly how the temperature affects the rate constant in this in Arrhenius equation. So the Arrhenius equation actually tells you how the rate constant, and of course the rate, because if you affect the rate constant, that's going to affect the rate of the reaction, is affected by increasing the temperature or changing the temperature. Okay, so this is the original form of the Arrhenius equation. What this relates, as it can be seen really easily, that the rate constant depends on a pre-exponential factor. Okay, this relates mainly the rate constant with the temperature, and these are the main factor that is covered by the Arrhenius equation is how the temperature affects the rate constant. Okay, and of course the rate. Okay, so this whole expression has to be remembered and memorized, and you have the pre-exponential factor. This pre-exponential factor depends on the collision frequency in a particular reaction. It also depends on the type of molecules that you're looking at and their orientation in which they collide. So it depends on very much on the shapes of the molecules that are involved in a chemical reaction. This has the same units as this. We will be covering that. We'll see how that is the case. A has the same unit as K. Now we'll look at what K's unit is. We'll recap on that in a minute. So we'll just look at the factors, the various aspects of the equation. Okay, so K, the rate constant, equals A. A is a pre-exponential factor. This is the exponential factor. So this comes before that, and that's why it's called pre-exponential factor. E, we'll look at what this is. This is a natural log constant. It's just a number. We'll look at what that number is. If it's, I don't think it's necessary. So all you need to know is just a number. We'll look at what that means in a minute. Okay, so then you have e to the power minus EA. This EA stands for activation energy, divided by R, the gas constant, and T, the temperature, should be in Kelvin. Gas constant is 8.31, and that's just a number. EA is the activation energy, and the unit is joule per mole. We'll look at the units in a minute, so don't worry about all that units. Just try to remember it's a general form of the Arrhenius equation, the original form. Okay, so that's the first thing to get out of. Let me rewrite that in a normal way, because it's best to write this out. I think K equals A e to the power minus EA, activation energy, divided by the rate constant and the temperature. The reason for writing that is the format is not very clear over here. Okay, so I hope this makes sense. Okay, so we're going to look at what this each part is. The first part of the equation is, first part of this video lesson is about looking at various factors and the units, and try to understand the original form and the rearranging of this and converting this equation into the logarithmic form. Okay, so let's have a look at the units here. You have we're going to focus on this bit here first, the activation, the exponential factor first, and then we'll look at the pre-exponential factor. So initially, let's have a look at the units for EA. So EA has a unit of, this is the activation energy. Its unit is joules per mole. Okay, so that is the minimum energy you need to get a reaction started. Okay, that is the energy required per mole of the reactant. Okay, so you have that unit for EA. Now R has a unit of joule per mole per Kelvin. And then we have the temperature T in Kelvin. Okay, so putting all these values in the equation, just this part here, so let's put the values in there. So EA has joule per mole. I'm ignoring the negative sign because I'm only considering the units, divided by joule per mole per Kelvin for R. So I've substituted the units for R, and then for Kelvin is it's just K, right? So temperature unit is just Kelvin. Okay, I don't know why I put the minus there. It's just K there. So this thing cancels out. The per mole to the power minus 1 cancels out. Joule cancels out. Basically, this means this bit here hasn't got any unit. That's why you have K unit exactly the same as this, because you have a number here. E is a number. This doesn't have any units, so the units of A is exactly the units of K. So for a first order reaction, if K has a unit of so if K's unit is per second in a first order reaction, then A will also have the same unit. That's what this means. To understand expressions involving logs and lns, so you'll come across logs and ln, natural logarithm, and that's log to the base 10. So to do this, you should be using in your calculator, you should be using the functions, the relevant buttons, which is over here. So that is the log to the base 10, and then that's the log to the base e, natural logarithm. So that's written as ln. Okay, so this is ln and that's log. So we're going to be using these two buttons. So when you have expressions like log ln 2.3 times 10 power 4, you should be using that button there. And if you see log, which we'll not be using this lesson, it's not needed, but just in case, so if you're wondering what's the two types, you should be using that. Say log 2.4 times 10 power 7, something like that. You should be using this button here, because this is a log to the base 10, and we'll see what that means briefly. And this is to the base e, so this is ln to the base e. So let's have a look at what this actually means. Say when you say log x equals y, this actually means x equals 10 to the power y. So this expression, so when you write log x equals y, this is what you're saying. 10 to the power of what gives you that number. Okay, so for example, let's put a number here to understand this a little bit better. Okay, so we have log. You can try this number in your calculator. Log of 100, let's say log of 100 equals 2. This means 100 equals 10 to the power 2. That's what it is saying. That's what it means. When you have log of 100 equals 2, you can actually try this in your calculator, and you will get this these values. Okay, you get 2. So what that means is, because it's 10 base, when you say log, this is to the base of 10, and normally not written there. That's what it means. So when you write log of 100 means you raise 10 to the power something and you get 100. So this question mark, or this 10 to the power whatever it is, gives you 100, and that number being 2. So that's what it actually means. Okay, so natural logarithm, which we write like this, ln, is to the base e. Okay, so let's do the same thing here. Ln x is y. Then if you rewrite that, We make myself some space. Okay, so let's move that away. So we looked at log to the base 10. We look at the same, it works the same way. So ln, which is now to the base e. Or you can say log, okay, so ln, it goes without saying this is to the base e. I will write just e just for clarification. Okay, normally you don't have to write that. Ln x equals y. This actually means x is e to the power y, and e being a number. What number it is, you can actually find that out by just pressing in your calculator, press the button e to the and do this, in your calculator you'll get that number. Okay, that's what it is. Okay, that is a natural logarithm, and this is log to the base 10. We'll be in this lesson using that expression. You don't need to know all these details, but some manipulation of log expressions are useful. So we'll look at that in a moment. It's useful to know these formula or laws, rules with to do with logarithmic functions or expressions is these. So when you have log to the same base, like 10 or e, it doesn't matter. Log of a number plus log of another one, you can rewrite this as log mn. You can actually try out this in using any number, and you'll probably you will get the same answer. So whatever this log m plus log n can be rewritten as log m times n multiplied by n. Okay, so you also need to know log m, take away log n to the base 10 or e, gives you log m over n. What that means is if you get an expression like this, you can simplify it like this. Okay, so that's useful to know for the next stage. So let's start with this expression here. As you can see, this is the original form of the Arrhenius equation. Now this can be rewritten as this. So I'm going to take a logarithm on both sides, natural logarithm ln. So ln k now equals ln a minus ea over rt. Now you notice this. So what you see here is the e is gone from this expression. What's happened is, when you take ln of e to the power anything, say ln e to the power x, this is simply x, so the e will be gone. Okay, so same works with the base 10 log as well. Okay, so ln e to the power x is just that number, and that's what's happened here. So you're taking a ln of this, and ln of this whole thing, and when you do that, this goes away, so the e goes away, and you get this term coming down. It's no longer raised to the power of e, it's just as a normal number. So the whole of the power of e is now just a normal term here, normal factor here. Okay, so ln k equals ln a minus ea over rt. This is the linear form of the Arrhenius equation. You should really familiarize yourself with both forms of the Arrhenius equation. Now, or if you know this and if you can convert that to the linear form, that's fine. So okay, that's we're going to need these two equations in this part of the Arrhenius equation, part 1. And that's a summary of what we have been discussing so far. We're going to move on to the use of this Arrhenius equation. A simple application and use of this equation. Let's have a look at this example here. Let's see what's given here. A is given the pre-exponential factor, EA is given the activation energy, R is given. Start with the original form of the Arrhenius equation. As you are asked to calculate the rate constant at 27 degree centigrade, the temperature is given as well. Remember, in the expression you have to use Kelvin, which is obtained by adding 273 to this number. Okay, so let's start with the original form of the Arrhenius equation. So having done that, you can pretty much see that you have all these values. You have a pre-exponential factor, you have activation energy given there, so you do have this number, so this value given, EA is given, you know what R is, a gas constant, temperature is given. So it's just a matter of substituting the numbers in. I think it gives real good practice with your calculator. So you may want to pause this video and then try out this calculation, check the solution, which I'm going to go through now. Okay, as you can see, I've just substituted the values from the problem in here, except I've used temperature in Kelvin scale by adding 273 to what's given here, and that is over here. So it's better if you can work out this expression in one go, but if you're not sure, do this part first, or even you can try just this part first and then do e to the power of the answer. So you should get this part here first. If you're not sure how to do the whole thing in one go, do this part first, so that part, and then you can do e to the power answer. Okay, so try that and then multiply that with 1 times 10 power 14. Okay, that gives you the rate constant. Try that in your calculator, see what you get. You should have got 8.7 27 times 10 power minus 10. Okay, so that will be the rate constant. This should have a unit of per second. I'm saying that because the pre-exponential factor and the rate constant has the same unit, so this should have the same unit. You should have this answer. However, this value here is given to two significant figure, so I'm going to round this up to two significant figures. 8.7 times 10 power minus 10 per second is your answer. Here there you go. We got this answer, but this is given to four significant figures. Let's have a look at this second example, which is slightly different to the first one. See here, you've been given the rate constant and the temperature is given. You are required to calculate this activation energy in kilojoule per mole for this reaction. Pre-exponential factor given, rate constant is given. You may want to try out the normal form of the Arrhenius equation, the original form. You will see that it has some, you can't, it's much easier to work with the other expression. So let's have a look. As you can see, the factor that you are looking for, the EA, is an exponential factor. It is the power of E. So to solve for E, to rearrange it and get it, is a bit tricky using this equation. So you're better off using the linear form of the Arrhenius equation. So if you rewrite that equation here, ln K equals ln A minus EA over RT, you can pretty much see that it is much easier using this expression to obtain a value for EA. So rewrite this equation, rearranging that equation, not rewriting. you want EA, so you can rearrange it like so. So you can have mm, minus EA over RT equals, so I'm bringing this ln A to this side, and it becomes negative, so ln K negative ln A. Okay, so you have that. Then you have a negative symbol here, so bear that in mind. So you can just use it as it is to avoid errors in this. Remember, you can rewrite this like so. Ln K take away ln A is ln K over A equals minus EA divided by RT. Okay, so just substitute the values in, or you can still rearrange this for EA completely. You need to multiply both sides by RT to bring that on this side. Okay, so you can multiply both sides by RT. So what do you get? You have RT, and you will have this cancels out, so you're left with just minus EA. So just do this, enter these values in the calculator, see what you get. There is a typo here, there is two, no, there's no 2 here, so K is just 6.51, so I'm going to use that value here, 6.51 times 10 power minus 3 divided by the value for A, 2.57 times 10 power 10. Okay, so that is the value to be worked out. That equals minus EA. So if you actually work that out in your calculator, you should have got 7 2 3 4 2.2, and the units are joule per mole for activation. So the activation energy. You can express the same thing in kilojoules, but mind you, it's better to put this in 3 significant figures, because in the problem you just have 3 significant figure values given. So you round that to 3 significant figures and convert that to kilojoules by dividing that by 1000. You get 2.3 kilojoule per mole. Okay, mind you, this was a negative number, but because this is equal to minus EA, so minus EA equal to this number. So when you have EA, you have to change the sign as well. Okay, so it's a positive value, and this is your answer. Okay, is the second example done. You can see in this example you have some data given here, temperature and the rate constants. You can see that the temperature, as the temperature increases, the rate constant increases as well. Okay, use the Arrhenius equation to calculate the pre-exponential factor at 290 Kelvin. So you're going to use these two values. So each problem is slightly different. You have to then decide which of the two forms of Arrhenius equation you're going to use. So in this case, because you're calculating the pre-exponential factor, you're better off using the original form, because the rate is given, the rate of the reaction, the rate constant is given. So you will see for yourself it's much easier to use this equation. Okay, EA over RT. When you are given this value, I think it's much easier to use this form of the equation. Try both, and you try writing both, and you should be able to see which of the equations is much easier to get the answer. Okay, so k is given, so I'm going to put the k here. 0.003. We want a e to the power minus 55. Remember, this is given in kilojoules, and these are possible errors people do make. For this expression, you must put the energy, activation energy, in joules. Okay, so you need to multiply that by 1,000. Okay, divided by R, 8.314 times the temperature is given as 290. Okay, another reason for using joules here is this unit is joule per Kelvin per mole, the value for R, so the units must match. So if you're using joules for part of the units for this number, you should have the same for the other unit as well. The units do have to match. Okay, so now all you have to do is rearrange this equation to get the A. Okay, so you may find it easier to work this out, this part here. So try and work this part separately and then bring that over here. So divide that number by this, you get A. Okay. Okay, so if you simplify that expression, you get this, and then e to the power negative minus 23 point. So the answer to that goes here, and that gives you this number, and then multiply that by A. So to solve for A, you need to divide that number by this, and if you do that, you would get this answer, which is 2.98 times 10 power 7, because this is the pre-exponential factor and it should have the same unit as k. K's unit is here. Make sure that you write the unit. Sometimes there is a mark just for that. Okay, per second. So okay, so that's what you should have got. Mind you, I have written this answer to 3 significant figure. That's because most of the values are given to 3 significant figures. There's 2 significant figure here. So yeah, 3 significant figure seem to be the most appropriate for this problem. Okay, that's why I've given it like that. Okay. Let's have a look at another example. This one being slightly different to the ones we've been slightly different. So we'll look at this one. You've been given a rate constant at one temperature, and then the rate constant is given again for a different temperature, slightly higher temperature. You'll also notice that rate constant increases here as you increase the temperature. So you're required to find the activation energy. Now, how do we do that? So here we do not know the value for A, so we're going to assume that does not change for the 2 set of conditions for the 2 different temperatures. We're going to assume A remains the same. So we're going to just use, we are using subscripts here, K1, which is because we got 2 rate constants. So I'm going to put K1 to represent the first condition, and K2 and T1, T2. Made 2 equations because we have 2 different temperatures and 2 different rate constants. I've kept A the same, assuming that A does not change with temperature. Okay, but it does remain constant over small changes in temperature. Okay, so we're going to we'll have to keep that the same. Okay, so then all you do is get rid of this by subtracting this equation from that one, like you do for simultaneous equations. So you can see how I've done so far. I've just subtracted the second equation from the first one. Okay, so what happens is this gets cancelled away. So you have ln k, this ln k1, take away ln k2 equals, this gets cancelled away, minus EA over RT1 minus of this value here. Because there's two minus here, this becomes a positive value, so I can write this part at the front, because it'll be nice to have a positive number at the front. Okay, so that can be written like this. You can see that I have simplified that expression, put the positive value here at the front, and then take away this value here minus this factor here. Ln k1 minus ln k2, I've written like this. You can keep it as it is if you want, because all you're going to do is substitute the value for k1 and k2 here. So you can keep it like this, or you can simplify it like this. Now, because A over R is a common factor, I've taken this out. Now, you can see you should be able to calculate activation energy from here. So all you have to do is substitute the numbers in and simplify it to get EA. So EA would be R times ln k1 over k2 divided by 1 over t2, take away 1 over t1. If you find that too hard to deal with, you might as well substitute all the values and actually solve for EA. That you would find it slightly easier. Okay, just put the numbers in for all these values and then solve for the unknown one by multiplying both sides by the value for R, and then find this value separately, divide the answer by that value. So you should get the answer that way. When you do this, you should remember to convert the temperature to Kelvin. Other than that, you can just put the values in here. You should get this answer. This is your final answer here. EA should be equal to 1.60, three significant figures, times 10 power 5 joule per mole. Let me check if you get this answer. Okay, and that should be your final answer for that one. Okay, the second part of the equation is asking you to work out the rate constant. This can be a little bit confusing because you've been already given two rate constants, two different temperatures. What this is asking you to find is the pre-exponential factor A. You don't normally get questions like this. So let's assume this is basically A. So how do you find the pre-exponential factor? So from part A here, you already have EA. So you're going to just use that equation. So let's rewrite the original Arrhenius equation. K, rate constant, A e to the power minus EA over RT. So you're required to find A, which gives the maximum possible rate constant. And that's what this is asking you to do. So pick any one of the values that's given. So let's use this value. So I'm going to put 5.4 times 10 power minus 4 times, so that equals A, we don't know what this is, e to the power EA from the previous part. We already know EA, so I'm going to just substitute the value here, 1.6 times 10 power 5 divided by 8.314 for the gas constant times the temperature. So I'm going to use this but convert it to Kelvin. So that's 599. Simplifying this and solving for A. So find this answer and divide by this answer. You should get A, which is equal to 4.73 times 10 power 10. Now the unit for this is the same as the rate constant unit, so I'm going to just rewrite the unit for the pre-exponential factor, okay, which is you'll find same as this unit here. Okay, forgot to put the negative here. You probably have if you use slightly different values for R and different approximation, you should probably this is another possible answer, 4.85 times 10 power 10. That's also okay, depends on what values you use for rate constant. Okay, so that's alright as well. So in this example 5, you are asked to compare the rate constant at two different temperatures. So the question is here, the only thing that is really given is the temperature change, R value, and you're asked to assume the activation energy is 50 kilojoule per mole. The frequency factor A is approximately constant for a small change. So what the question is asking you is how the rate of the reaction changes when you increase the temperature by 10 degree. Okay, it's best to compare the rate constant for the two different temperatures. Okay, so if you consider both forms of the equation, K equals A e to the power minus EA over RT is 1, and the other logarithmic form is ln K equals ln A minus EA over RT. It is obviously it's really obvious which one to use. I don't know if you can see this. If you want to compare the rate constant, it's much easier to use this equation because if you do use this, you'll only get a ln of the rate constant, and then you have to convert that to just K to compare them. So let's use this, and you'll see why as we progress through this question, why we chose this equation. Okay, so K for the first condition, 20 degree. So I'm going to just substitute the values as it is. So K at 20 degrees. So you may want to put K1. This K1 is the rate constant at 20 degree. Because A is the same in both cases, you can just ignore that. So the only factor we're going to compare is, use is just the E. So we're just going to compare the exponential factor only. In fact, strictly, this is not K equals. K is proportional to, let's say we use that symbol there. So E to the power minus EA over RT, we're just going to use that one, but we're going to use temperature 1, and then for the other one we'll use temperature 2. So K2 would be proportional to EA, the activation energy, divided by RT2. Okay, so we're going to just put the numbers in, and for this value here, so this expression is the only thing that we're going to use to compare. So let's put the values into that expression. Okay, so EA is 50 kilojoule per mole. Notice that this is given in kilojoules. We have to use joules to match with the units for R. So it's for temperature T1, which is 20 degree, this would be e to the power minus 50,000. I've converted the kilojoules to joules, divided by R, which is 8.314, times the temperature has to be in Kelvin. So 293, I'm using 20 degree, 20 plus 273 gives you that 293. So if you work out this value, it comes to this 1.2187 times 10 power minus 9. And if you do the same calculation using 30 degrees, same activation energy, and using this expression K2. So we are looking at the same factor, which is the E exponential factor, because the A is going to be the same. So if anything, rate is going to be proportional to that. So apply these values into this exponential expression in the same way as we did just now. What you get is, you get this. So in the second case, so this is K, this is K1 proportional to this. K2 would be A multiplied by this factor, 2.399 times 10 power minus 9. Okay, so you can see that the K has now doubled in value, roughly. So you can even divide this value by that to see how many times it's increased. So I get roughly it's 1.97 times. 1.97 times it's increased. So K2 is 1.97 times K1. So K2 would be 1.97 times. So it's roughly doubling. So what this shows is, when you increase the temperature by 10 degree, you can see the rate of the reaction doubling in value. That's what this is showing. Okay. So here is a task for you to try out. It's a 3-mark question. For this, you're given the rate equation. Look at all the information that's given. Try this out. The solution follows, but pause the video and really try this out for yourself. So in this part of the question, you will be using the your answer from the previous question. This is the equation that's given to you. This Arrhenius equation in the logarithmic form. Use your answer from the previous question to answer this. Okay, and try this question before you go any further. So pause the video. Try this. Use the ideas that you've learned through this video. Calculate the answers and then check the answer. Here's the answer and showing the working out as well. Pause the video, check your answer, your working out with this. That is the answer to the part 2 of the question that you've been given. Check your answers. Hopefully you have got that right. Well done if you got that right. That is the end of part 1 of the Arrhenius equation. And then we'll look in the graphs and how the linear form of the Arrhenius equation is used to actually change variables, experimentally construct a graph, and from the graph you should be able to obtain EA, the activation energy, or other missing values from that. Okay, so we're going to, and also so EA and also pre-exponential factor, two things that you can get by just constructing a graph. We'll look at that in part 2 of the Arrhenius equation.